Everyone got to meet the people. Yeah, I appreciate the invitation. I really have enjoyed my time here, so thanks a lot. Yeah. Right. So as he said, my PhD was completely unrelated. I've talked with some of you about that today already, but what I'm going to talk about today actually goes back to what I started. When I shifted gears during my postdoc. This is kind of an arc that goes all the way back to when I started that a thread that I've been carrying through this entire time. So this is work that has at some point, I haven't even tried to list all the people. There's been kind of a constant presence of a postdoc and or a student who's been working on this throughout with funding from NSF and then most recently ONR as well, which I'll kind of comment on as I go. So this is a video that I like to show to motivate the problem. I got this from Byron Blomquist from the High Wings campaign. So this is the North Atlantic, so this is not a hurricane. In fact, this is 27 meter per second winds, which is not yet Category 1 strength. So this is tropical storm strength, although again, it's not even in the tropics. But the overarching question is, how do we understand and parameterize air-sea fluxes in this sort of environment, right? So, you can see spray being ripped off the top, the turquoise color, these are bubbles being injected into the surface. And so you've got waves sort of on top of waves. And so, where's the breaker? Is it the whole thing? You have these smaller ones on top. You have these streaks which are forming and so on and so forth. And the question is how much momentum is being transferred or how much drag is there at the surface? How much heat and moisture is being transferred? And then High Wings, I don't know what it stands for. I think the G stands for gas. This was, how much gas transfer is going on at the interface as well. And again, so you start to run into questions about, what do the bubbles and the spray do? How, what do the waves do? How do you model all of that? For a tropical cyclone or hurricane, one of the ways, so this is some work, I did not run these. This is done by a colleague of mine, George Bryan at NCAR. But my student who just graduated, Chibueze Aguijafor, kind of took it and was doing some analysis of the turbulence inside it. So this is large eddy simulation. So this is 30 meter resolution simulations of the inner core of a hurricane. And so, as far as atmospheric flows are concerned, this is really, really high resolution. But aside, right, this is kind of an idealized test case. This is, research grade code and so on. But in reality, a lot of times what we're doing, when we're simulating hurricanes or we're modeling hurricanes, we're trying to do some sort of forecast or prediction. This is, the cone of uncertainty for Hurricane Dorian back in 2019. It devastated the Bahamas. Was it the Bahamas that it parked on top of? I can't remember now. Do you remember? No. Okay. No. Bermuda. I think it just sat on top and caused all sorts of destruction. But either way, whether you're doing something like this and you're trying to get really high resolution and see what some of these individual features are, or if you're just trying to do sort of a more coarser scale, but you want to know how strong it's going to be and where it's going to land and so on, the common theme is you need boundary conditions at the bottom. And so one way of saying, I showed the video of waves and spray and so on and say something about fluxes, but in practice where that comes up a lot is, all right, if the bottom of your computational model is this flat surface sitting down here, your first grid point is 25 meters or 100 meters or wherever it might be. Again, it might be close, but it might be far away from the bottom surface. But either way, you're not resolving the spray or the waves or anything like this. Typically, this is a common way of parameterizing this. You say, all right, tau, H, E, K, you can kind of combine H and E into K, a moist enthalpy. That's what you want to know. So your boundary condition is how much momentum, how much stuff is going in and out the bottom, how much momentum, again, that's the drag, but how much sensible heat and how much latent heat. And so a common way of parameterizing this is just through a flux coefficient, right? So a drag coefficient, CHCE, these are scalar transfer coefficients. And so what you do is you have some reference velocity. Let's look at this one for a second. UREF would just be the velocity at your first grid point. You say, all right, I know the velocity of my first grid point. I will then from that multiply it by some drag coefficient to get what the surface flux of momentum would, is, right? Again, trying to take into account all the complex physics that might be going on. The same goes for, the sensible heat flux or the latent. Here, you're going to take the difference in the temperature at the surface, at the sea surface, minus, whatever it is at some reference height. Typically a model like these would be your first grid point and so on and so forth. So the question becomes, well, what are these then? This looks great. These are grid quantities or boundary condition quantities, but what are CH, CD, CE, and so on? And before I kind of get into that, does it matter? I mean, if you're looking at hurricanes in particular, or tropical cyclones, how sensitive is your prediction to whatever you choose for these things? And there's a famous result by Kerry Emanuel that kind of begun in the 80s and kind of summarized in this 1995, and they've developed it since. But what this shows is that, so Vmax is the maximum wind speed of a hurricane, all right? So that's typically when you look at a hurricane or when you see one reported, the strength of it is either given to you in terms of like a wind speed, like a maximum sustained wind speed, or a minimum pressure inside the eye. And so, that's two ways of characterizing it. So if you look at the Vmax as a function of the ratio of CK over CD, so CK is kind of this enthalpy flux coefficient. What he showed kind of theoretically, he kind of conceptualizes a hurricane as a giant heat engine. So, all right, you have stuff coming in from the bottom, right? So the stuff coming in, the heat and moisture, leads to buoyancy, which is kind of energizing the storm, right? So you get a lot of thermal, sensible, and latent energy coming from the ocean to power the storm. And the drag, represented by CD here, is what slows it down, or something that slows it down. And so the stronger you make CK relative to CD, the stronger the hurricane is going to be. And he found, this kind of classic result, again, kind of doing a bulk energy budget of a hurricane, it goes up like CK over CD to the 1/2.
So those parameters on the previous slide, would those go into like a wall model based on like a law of the wall or something?
Yep.
Or
Yeah, they don't call it that, but yes, it's a wall model.
Okay, and so you usually presume some boundary layer profile for the not only momentum but for the temperature and energy.
Sort of, but you have to realize that for something like this, there is no bound. I mean, the entire boundary layer is all. I mean, the first grid point might be well above 500 meters, and so you might not even be resolving anything. So you have a boundary layer scheme in addition to.
Right, but that's why you model that unresolved boundary layer, right?
That's right, but I don't think they would ever actually explicitly say like, here is the shape of the boundary layer. That's probably embedded somewhere into the boundary layer model and the Lancer or the rough.
So these parameters are just going into the boundary conditions somehow.
Yeah. But I mean, you are right. But I think those details are embedded deep within the assumptions made in this. But like in practice, it's often just these are just sitting there in the code. And like I said, so CK. The prognostic variables are typically like a temperature field, a water vapor field, and a momentum field or a velocity field. Moist enthalpy is not typically carried around itself, but it's often assumed that CK is the same as CH and CE, which is another sort of assumption that we can question at least. And then there's been a whole bunch of studies. Just does it matter? Again, how sensitive is your model to choices of CK/CD? How accurate do you need to be with this? How worried do you need to be if you're not resolving things like waves or spray and this kind of thing? There's people who have done, all right, the different lines here are just different choices of CK and CD, looking at the evolution of a storm, so it matters a lot there. Some don't actually intensify, and other ones do, depending on your, how your choice of CK and CD. Others have tried to use parameter estimation and go backwards. They run these ensembles of a bunch of different values of these things and try to get a sense of, which of these are giving you the most realistic behavior of the overall storm and that kind of thing. So what are they, right? So how would you actually go and get these? I mean, how would you come up with what these flux coefficients are, or these roughness lengths, if you want to cast it that way? So on the top left here, this is a famous paper by Powell et al. In Nature in 2003. So I'll start by kind of just commenting maybe on this black line here. This black line is the quote Largen pond curve. And so this is the drag coefficient. It's kind of weird. I'm talking to engineers now. It's a non-dimensional drag coefficient versus a dimensional 10-meter wind speed. Okay, because to turn this into like a Reynolds number is not a typical thing that you would do. At low winds, there's a lot of measurements from a lot of different platforms and wind tunnels and so on. And the black line is basically just extrapolated from that. And so the Largen pond curve is sitting there, and it was kind of becoming well known that doing that out beyond 40 meters a second really took way too much momentum at the bottom. It would grind these storms to a halt. And Powell, and using a technique which I'm going to detail in a few minutes, these are the hollow symbols here, showed or estimated, it's not a direct measurement of the flux, but estimated that the flux coefficient seems to actually saturate and maybe even start to go back down. And this was kind of a big deal. Several years later, another group did this, but actually he did this using dropsondes, like air, atmospheric measurements. Someone else did this using ocean measurements. And so you take ocean measurements and try to piece together a momentum budget to say something about how much momentum must have entered the water column. And they got something that kind of looked similar. And then once this started to be kind of recognized as a possibility, then a whole bunch of models showed up. And I'll say more about this one in a second. But models like this said, oh, here's what it used to be. And then here's, if you use our modeling strategy now, you get these, where these points are basically the same points up there. And the question quickly became for me, and this is kind of where I entered this field of like, well, is this right? I mean, are you getting that behavior for the right reasons? I mean, for the right physics? The enthalpy flux coefficient, I'll start up here. This is a model. So, this is a spray model from Ed Andreas, who kind of did a lot of work in this area. So this black line is what he calls interfacial, which I'll say more about later as well. But that's just the surface. If you took away any sort of spray droplets, that's just how much heat and moisture flux you get off the surface, and it stays relatively constant. And if you add spray, you get of different ambient temperatures, you get these different curves right here. This is another model which kind of shows something similar. These lines really ramp up. The idea being that spray can really take it away. This is another collection of these points right here are actually mine from using some estimates. These are some bulk estimates as well. These curves right here are laboratory measurements. And so there's some discrepancies here. But when you start to piece together, so there's a lot of efforts trying to figure out what these flux coefficients are and how you would parameterize them and put them into the bottom of one of these forecasting or largely simulation models. But then the more you look at these different attempts at measuring what these are, estimating what these are, you start to see some contradictions. So first, if you look at for the enthalpy flux coefficient, right? Or you could just think the scalar flux coefficient. There are two, a lot of people think that spray might enhance this, okay? And so both of these are qualitatively showing. So forget these two curves up here. If you just look at the black and the blue curve, that's the enthalpy flux coefficient as a function of wind speed that's the blue, and without spray. So again, it's kind of flat. Both of these would say that it's flat without spray. You add spray and the coefficient itself starts to go up with wind speed for reasons I'll hopefully be able to explain later. But what I want to draw your attention to is that look at the scale. So this goes up to about 1.5, 1.8 times 10 to the minus 3. This goes up to like 4. This isn't, these points at 40 meters a second aren't even on this axis, right? This would be up here somewhere. And so there's this massive difference in what these two spray models are saying that spray would do to the flux coefficient, which, okay, I mean, which one is right and under what circumstances might one be more right than the other? With a drag coefficient, again, there's this famous paper in 2003 which says, oh, the drag coefficient might actually roll off and actually start to decrease rather than continuing to increase if you just extrapolate from low wind speeds. And so then one group, in 2007, they come up with a wave model. They say up front, they make the assumption that, well, this saturation of the drag coefficient is coming from aerodynamic smoothing of the surface, right? So waves are getting sheared flat. You're doing something to the wave spectrum that actually leads to, a saturation of drag coefficient. They have a model with some parameters and they fit it and they tune it. So they're saying that this effect is coming from waves. Meanwhile, there's other groups which say that the saturation of the drag coefficient is coming from spray, and there's some explanation as to how it might do that. After 10 years of working on this, or more than that, I actually don't think spray has anything to do with the change in the drag coefficient, but there are models out there which exist, which get a similar looking shape for a completely different reason. So again, when I encountered this, it's like, these can't both be true, right? It could be a combination of them, but they can't both explain the rollover at the same time. Then if you look at wind tunnels, right? So there are wind tunnels. This is a really nice paper. This is done at the Miami wind tunnel, the kind of the precursor to the sustained wind tunnel, if you've been there or if you've heard of that. It's sort of like the one that Martin showed me this morning over in the MHL building. But they were able to look at the heat budget of the water, so track its temperature, try to insulate the size, and then again come up with how much heat must have left the top, and then come up with an enthalpy flux coefficient that way. This combination of sensible and latent, and they saw that there wasn't much variation with wind speed at all, like out to 40. another wind tunnel in Japan, basically the exact same setup, very, provocatively, I don't know what to call it. They get the exact same results. It looks about steady out to exactly where these ones end. So the magenta hollow symbols are these symbols here. And as soon as you get to that wind speed, it goes up. And that seems to disagree with some bulk estimates that myself and others have put. These are coming from outside measurements, which again, I'll explain in just a minute, which would suggest that, that it remains unchanged. So again, which is true? Is this an artifact of it being inside a wind tunnel? Why, what is going on here at that wind speed that this one, I guess, didn't get to high enough wind speed in this one? So that's all kind of an overarching introduction to say measurements are really difficult in these environments, as that video at the beginning hopefully demonstrated. Are the laboratory measurements representative, and how reliable are the observational estimates? And I haven't really described how they've done them, and I'm going to describe one of them and how we kind of want to do it moving in the future. And then another question that I want to focus on is, what role does spray actually play? Because again, I think there are bodies of papers out there which say, oh, spray is the reason that the drag coefficient level's off. And I think they're wrong. I mean, and in fact, in some cases, what they're saying physically is going on, I don't think could possibly be true. And so I want to use some sort of idealized but physics resolving simulations, right? So these aren't simulations of the full-blown air-sea interface, but they're idealized test beds to kind of test some of the assumptions in the spray models and try to understand some of the uncertainty in the estimates that we're getting from outside. That's kind of the twofold goal of what I'm going to talk about. Is everyone on board with that? Okay. All right, so number one, how reliable are the observational estimates? So any storm, any hurricane that is anywhere near the east coast of the United States, like the Atlantic or the Gulf of Mexico, I guess, am I allowed to say that anymore? The Gulf of America, I suppose. I actually know what the rules are with that.
According to Google Maps and Apple Maps, it's Gulf of America.
Yeah. Okay, so the Gulf. NOAA will fly their P3 hurricane hunters out there. And they go out there and they make all sorts of measurements. They have, tail Doppler radar, they're making flight level measurements, and among other things that they do, they drop these things called drop signs. Drop wind signs. And they're cardboard tubes attached to a parachute. They launch out the belly of the plane, and as it falls at about 10 meters a second, so it's in the air for 10 minutes-ish on that order, it's measuring temperature, humidity, wind speed, and pressure as it falls down. So you get a profile like this, so that it's launched from 2,000 meters or 2 kilometers upward at flight level, and as it falls down to the surface, it's giving you a recording. It's a quasi-vertical profile. If you're near the eye of the storm, like if you're in the eye wall, it can actually, it can wrap around maybe even like half of the circumference of the storm, but outside it's roughly vertical.
This is the magnitude of velocity, or is this the?
This is the magnitude of the wind speed. This is the square of the square root of the sum of the horizontal components. Square of the horizontal.
Oh, so it doesn't have any of the vertical components.
It does not have vertical components. No, it does not have the vertical component, and you can try to back it out. And a friend of mine, colleague has done that. During the QCing of dropsonde data, if you get elevations which go up, right, it's supposed to be falling, and it's assumed that it's falling at 10 meters a second. And the software will eliminate anything that has, like, if the altitude goes up in time, it just nixes it. And what he was looking at was like, no, you can get updrafts of 20 meters a second. And so he could actually carry this up. And so he went manually back through to look for these cases that had been excluded for that. So you can kind of get a sense of what the vertical velocities must have been to get extreme events like that, but it does not have a reliable vertical speed.
But you know the 2 horizontal components?
Yeah.
You can't just assume divergence free.
No, I mean it's compressible. The atmosphere is weakly compressible, but the density is changing with height, so it's you could do like a Boussinesq or an anelastic approximation or something like this, I suppose. So this is horizontal wind speed magnitude, but you do have the 2 components. It does break it into sort of latitude, longitude, and then with the temperature or potential temperature and water vapor, you can construct, you can do profiles of either those, or you can combine them into a single like moist enthalpy, which is combining, which is a little bit different than enthalpy like you'd see in a sort of a heat cycle engineering class. Okay, so then what we do, and this is just following that Powell paper that I referred to a minute ago. This is what he did, and this is what we started just copying. You construct mean profiles and you invoke Monod-Nabokoff similarity theory. But for this audience, this is like the Clauser method or like the Kappa method. Basically what you're doing is you're gonna construct a mean velocity profile. So you take each SON, each profile, and there's been, we have a database of like 20,000 of these that have been dropped since 1997. For each one, here's your wind speed profile. You come up with some criteria with which to categorize or bin it, right? And so what we did, just copying Powell, was we took the average boundary layer height in these hurricane boundary layers is about 500 meters. So we take 500 meters downwards and we just compute the average wind speed. That's a number. And then we say which, does that fall into 20 to 30, 30 to 40? Which bin does that fall into? So you take all 20,000 of these SONs, you put them into the buckets, and then once you're done doing that, then you average them all together. And if there's a log layer, MO theory or just log layer theory would suggest that you'd have a straight line if plotted on a semi-log plot. And remarkably, I say remarkably because I didn't really expect this to work out so well, but you get something that looks awfully logarithmic. And then, according to MO theory, the slope of this line would be kappa over U star, okay? And so, here's your law of the wall, right, or your log layer. The mean velocity has a slope of, U star over kappa, or however, depending on how you're doing it, which is logarithmic with height, and there's some roughness length. You can do the same thing with the scalar, right? I'll point out that the scalar, you need to know something about the surface condition. Okay, that shows up. We're assuming that the surface current is small compared to the wind speed in the atmosphere, which I think is reasonable, but actually the project that we have now, we kind of want to test this. So you fit this line, you get U star. Once you know U star, now you can just directly get tau. That's what you need to know. You want to know the momentum flux, and you can do the same thing with heat, moisture, or enthalpy. All right, so there's this equivalent parameter K star, which shows up when you do the, when you make a profile of K, when you average them all together, and you can fit it, and the slope of that line is going to give you K star, and you multiply U star and K star, and you have this. And then you can back out what the drag coefficient is by defining some reference state. When you want to get the enthalpy flux or the other ones, you actually have to know the reference state as well as the surface. And that's problematic because the drop SONs don't measure the sea surface temperature or any properties of the sea surface. So what I do in just a minute is we interpolate from satellite, like daily satellite products. And so that's questionable how accurate that could be. There's some cool technology that they're trying to develop where they have an IR sensor on the SON, which is trying to look down and get the temperature before it hits, and some other things like that as well. So, oh yeah,
Is Z not some kind of like wave field?
it would presumably have something to do with the wave field. Yes. So you can also fit that, by the way, right? You fit this line, and your two parameters are basically U star and Z naught. So I could plot. So we plot CD. I could equivalently plot Z naught versus U10, which is actually, one of the codes I use is called CM1. What you prescribe is actually the roughness length, not the drag coefficient, but they're typically assumed to be related in this way, right? And Monod-Nabokoff, you can put stability corrections, like so buoyancy corrections, but still, in principle, you'd still have this. These are your two fitting parameters when you fit this line, basically. So this is a paper that I wrote with Dan Stern and some others in 2016. So CD, the drag coefficient versus U10, the black and the red dots right here those are the Powell results. So they kind of followed up and did some additional analysis in 2012. It's basically the same. My results are the blue and the magenta, which track right along them, which of course they do because we're using the same technique on more or less the same data. So of course we get the same results. The yellow lines are what are called like direct flux measurements. This is like computing the correlation U prime, W prime, but from aircraft flights outside of the eye wall. And so, it's limited to kind of low-ish wind speeds, and it's also being taken at like 500 meters, which it's questionable whether or not that has to do with the surface flux. The green dots are from Bell et al. These are coming from a whole combination of measurements, but then basically doing an angular momentum budget, and then saying what the surface drag must have been in order to conserve angular momentum. on sort of a storm scale budget. And so we see something that looks in there. And the purpose of this paper, the reason I have these two colors was to say, all right, this procedure of binning, averaging, and fitting, there's a whole bunch of choices that you, the user, would have to make, right? So how, over what height do I fit? What definition do I use to bin? And what we try to do is just distinguish between what we call natural uncertainty, just like sort of, I don't know if it's epistemic or aleatory. I never know the difference between those. Which one is like the one that's just kind of present that you can't do anything about? Whatever.
I would just ask Schwinn down the hall.
Okay.
What is that?
You know, method parameters is just, look, if I did this way and you did it a slightly different way, you chose to fit over a different height, how different would our answers be? Because they're MO theory, it's just like, oh, it's roughly this, and it doesn't tell you what height that this will stop being valid or anything. And so we start to get error bars like this. We computed CK, and so we too see, it seems to say that it's pretty insensitive to wind speed, which seems to agree with these are the wind tunnel measurements at Miami. It seems to go right into these other completely different budget estimates from Bell et al. But the error bars are huge. I mean, we're saying that CK could be anywhere between 0, which is probably not, or double what it's typically set to, which is not entirely helpful, but it doesn't seem like it goes up to 4, which is like what that spray model would have suggested. So then several years later, what we did was we said, all right, using those high resolution 30-meter LES of the inner core of the hurricane, George Bryan and Dan Stern, they launched virtual SONs. So you got this, you know, this time evolving, highly resolved field. You can launch sort of Lagrangian tracers, which just have a constant vertical velocity of 10 meters per second downwards, and then they advect horizontally, and they can launch like 100,000 of them into a single simulation. And I said, oh, give me your virtual SONs, and I will just process them. I'll do the exact same procedure, binning, averaging, fitting, but now we know exactly what the drag coefficient and the enthalpy flux coefficient were, because that's, I mean, you prescribed them in the model. So we did it. Rather than doing it by binning by wind speed, we actually binned by location. RMW here is the radius of maximum wind, which is kind of, you know, where the somewhere in here where the wind speed is highest. So we binned it by location, right? So the bins are basically like, you know, azimuthal rings. We have to avoid the surface because there is a wall model involved and we don't want to kind of contaminate. We want to fit over where we think the turbulence is actually being resolved. So that's where the black lines are. So it's kind of a narrow band, but what we see, so here is CD versus wind speed and U star, which is kind of the same thing, versus wind speed. And what we see is that it sort of gets close. The dashed line is what is actually prescribed inside CM1. But near the RMW, you start to underpredict it, right? And especially as you start to get like inside, you know, at and inside the eye, this starts to break down. And I want to point out too that there's really no reason to have expected log layer similarity to work here, right? I mean, you think about what's going on. I mean, the log layer is like unidirectional flow, you know, smooth. I guess it works for rough surfaces as well. But I mean, you've got massive radial pressure gradients, centrifugal forces. I mean, there's other body forces involved here that they could very well invalidate this. And it seems to be that despite it being logarithmic, at least qualitatively, it's not, you know, the slope of that line isn't necessarily telling what the surface flux is. Okay, so this seemed to suggest that, all right, is this real, this roll off here? At high winds, if these high winds are near this, you know, in the eye wall, is this drop off actually real? And another thing we did, and this kind of came accidentally, we said, okay, we were trying to see, you know, why are we even slightly different from theirs? And so I told my postdoc at the time, I said, okay, go back to the database and only use, I mean, because we're doing this 10 years after even the 2012 one. So go back and only use the hurricanes that they would have had access to at that time, and let's see if it matches. And then I said, go back and then do only the hurricanes that have happened since then. And she came back and, you know, so, okay, the first one we got really close to theirs because again, now we're using the exact same storms. And the second one actually went up. I thought, wait a second, that doesn't make any sense. I mean, like the total average seemed to go down, and that's these blue and magenta curves here. So what we did was just kind of say, all right, let's, of the 20,000 dropsons, let's just take random samples of them, right? And so like this is just kind of a brute force, like I'm going to take whatever, 20 divided by 3, a third of them, and I'm gonna randomly grab a third of them and then do the whole process and then plot it, and then do it again and do it again and do it again and do it again. And this is the range of CD when you just simply subsample these things differently. And it's like qualitatively, it might not roll off. And then we have this, and there's some other evidence too to suggest that at high winds, this procedure underestimates what the true drag coefficient might be. So this might not be real. And anecdotally, I've talked to several people who say, yeah, when we actually have this thing go down, it seems to give unrealistic forecasts or simulations of the hurricane. It works better if they keep it flat. Okay, what about spray? So again, here's all these ones that say, if you look at CM1, if you look at a lot of models, it's just set to like 1.2 e-3. That's just kind of what the coefficient is set to. I mean, what's going on here? There's absolutely no evidence that the CK ramps up to something like, 4. Again, that's like up here by 40 meters a second. There's absolutely no evidence that suggests that that's happening in reality. And so what's going on with spray? And so now, all right, now I'm kind of shifting over to the second part of the talk. The second question that I posed at the very beginning is, at the interface, again, there's these models out there which say, one kind of, I would say, caricature way of saying is like, all right, you've got this warm ocean surface, you have wind blowing over the top. Forget for a second the waves. That complicates things certainly for the drag coefficient because you have form drag, but for a scalar flux, the waves might not even matter all that much. That's kind of this interfacial transfer. But if you bust up the surface into a whole bunch of suspended droplets, that's just a whole lot more surface area with which to transfer heat and moisture. And that's kind of the basis on which this model's designed. And I'll get into that in just a minute as well. But again, there's not much evidence of this. But using this method of fitting these log profiles, we said, all right, wait a second. CK itself is quite uncertain because we don't know what the surface condition is. Why don't we actually look at HK, the actual flux itself? We'll just fit the line, we'll get this K star value, we'll get the U star value, and we can just compute this directly. So this is HK, this is now the dimensional in watts per meter squared, the dimensional flux of moist enthalpy versus U10. And what I'm plotting here, all right, so the green is those bulk estimates, using the budget method in actual hurricanes. The blue is mine. The magenta is those direct measurements made from the aircraft flying at 500 meters. And the blue, the light blue, is wind tunnel. And what do you see is different between them? The slopes of these lines are way steeper than the slope of the line that's coming from the wind tunnel. And if you go back to Andreas's model, this one that goes up to 4 times 10 to the minus 3, what he does is he says, okay, the interfacial flux uses this algorithm, which I won't get into, but basically, if you did a heat convection study, the flux would go up sublinearly with wind speed, right, or Reynolds number, if you want to think of it that way. Whereas the spray flux, according to his model, goes up like U star the wind speed Q, because you get more and more spray being generated with higher and higher winds. And it goes up very nonlinear and it goes up very, very quickly. So what I did is I took his model, right, the model that he produced here, I set it to predict the conditions inside the wind wave tank of this. And what you see is the red line is what the model would have predicted for the interfacial flux. And it seems at least to track exactly the same slope as what they're measuring in the wind tunnel. And the spray mediated flux, this gray line down here, seems to actually have the same slope as a lot of these sort of quote outdoor measurements. And they're converging right where the wind speed ended inside the tunnel. So what I think is happening is that in the tunnel, they're blowing spray out the back. So what they're not accounting for that really. They try to estimate that it's a kind of a negligible or a small amount that they're missing in the overall budget that they're doing. But from this, it certainly seems like the signal that they're measuring is all what Andreas would call the interfacial. And that even in a situation, right? So even when the flux coefficient is the same, this would seem to suggest that the scaling, the increase of the flux with wind speed is actually indicating that spray is carrying a lot of that enthalpy flux. So it's not doing nothing, it's just not changing the overall, the flux coefficient, which is interesting, which I'll say something about as I wrap it up. Okay. Yeah, I'm gonna have to start making choices about what I'm gonna skip because I'm taking a while, but I think that's fine. Okay, so let's look at the question of sea spray, right? Because the point of this is to say that there's some evidence from the dropson measurements that spray might be doing something, even if it's not this big dramatic increase in the flux coefficient. So if we look at this, waves breaking and bubbles bursting and so on, it's a really complicated process. You can think back to that video that I showed at the very beginning. Andreas, kind of one of these models that exists, kind of conceptualizes in this way. There's this interfacial, which is just kind of what the surface of the ocean would be doing in the absence of any spray. Then you have spray droplets, which are doing this complicated thing of, they're exchanging latent and sensible heat. And what you really want to know, though, you don't care about this, you just want to know what the totals are coming of sensible and latent coming at the top of some layer. And he's not the only one to break it up this way. There's Farrell in 1994, basically the exact same picture. And so what we did, this is my first PhD student, Tianze Pang, who worked on this. And what we did was we said, all right, let's not try to do some complicated, wavy boundary layer. Let's take a box. And we've done this in actually different configurations, just parallel walls, couette flow, channel flow, open channel flow. We've done all of these for different reasons, which I won't get into. We're doing DNS, the carrier phase. So we're talking like RE tau of like 300, 600, which is nothing. It's absolutely nothing compared to what's going on outside. In a hurricane. We're using Lagrangian point particles, which can evaporate and condense, exchange heat and momentum with the surroundings. They're two-way coupled. And so we'll just run it with no particles, and then we'll run it with particles. And it just say something about, here's what the droplets can and cannot do in terms of transferring heat from the bottom to the top in this kind of configuration. So it looks something like this. Again, low Reynolds number because it's DNS. You got particles being flung around. This is just to say that we're kind of conserving any momentum, heat, or energy gained or lost by each droplet is being projected onto the surrounding nodes, so they're talking to each other and so on. But these are pretty standard methods. And the goal was in this kind of a configuration to say, okay, let's directly test these so-called bulk models of Andreas and others to see if these even make physical sense. So that's kind of where we're headed. So what is a bulk model? Again, what Andreas and others have said is like, all right, we'll take the total flux, whether you're talking about latent or sensible, we'll break it up into spray and interfacial. Spray and interfacial. A droplet will come up, a single droplet coming up, it'll take some tortuous path and then fall back in. And the key here is what they do is they say, forget the trajectory. The bulk model, the idea behind the bulk model is I don't even care about its trajectory. What I'm going to do is I'm going to assume that it goes up and then comes back in. So it's quote re-entrant. Okay. And as it does, I'm just going to keep track of how much mass it gained or lost and how much temperature it gained or lost. So I'm going to mark what it was at the beginning and mark what it was at the end. And then once you have those two quantities and then you sum across all droplets that have participated in this, that you get something about how much total latent and sensible heat has been transferred. And so the spray flux is going to be a sum of these things weighted by some unknown coefficients. That's the general idea. Right? And so, we can do this. Farrell, like one model, basically says in this formulation, kind of uses a theoretical understanding to say that, well, gamma's got to be 0, beta's got to be 1, and that's what the total flux would be. Andreas fit to some observational data and came up with a beta, this parameter is like 15, and gamma's almost 2. Right? And those are just empirical fits that he got. Trying to fit low wind data. And so it looks something like this, right? And so in both of these models, you have to make some assumption about what the temperature change or the radius change would have been, and then sum it across some number of particles, which is its own problem, which I won't get into here. But the key here is that we can do this. So in the DNS, we know exactly what delta M is. We can track delta M, we can track delta T. We can compute these fluxes in exactly the same way that they're proposing this model in this idealized setup. So we don't have to worry about spray. We can just directly test whether the conceptual center of this thing makes any sense. And what we find is that beta has got to be positive, but gamma has got to be negative, right? And it's because it's really just because when it evaporates, it cools, right? So you have this competing effect, which Farrell had mostly right. Andreas, I think, had completely wrong because he's more or less double counting the amount of heat. So the spray droplets can't increase both the sensible and the latent heat at the same time because one has to come at the expense of the other is what that negative number is starting to tell you. And in fact, the cancellation is larger than or more severe than what Farrell had kind of reasoned through documentally. Okay, so that's kind of a very high overview of what we had tried here. So then we go back here and we say, all right, but we still have these unresolved questions about, so what's going on? That's this, we zoom in with DNS to say something about the bulk flux model, but still we have measurements which suggest this is CK, some laboratory measurements which suggest it goes off the rails up here, other estimates from outside which make it seem like it does this. Again, does the drag coefficient go down? Does it continue to go up? Does it level off or what? And so what we want to do is, rather than a small DNS box, we're going to zoom out and do a large eddy simulation of the full hurricane boundary there with the spray droplet. So this is what George Brown likes to call the complex LES. And then in 2017, he developed what he calls the simple LES, which is, let's design a patch. So this is now our domain. It's about 5 by 5 kilometers, something like this. And it's being forced, he estimates large scale forcings as though it's sitting with a centrifugal force and a radial pressure gradient force that would say that it's just outside the eye wall. It doesn't work inside the eye wall, but somewhere outside. Okay, so we have a 2D periodic box, which is meant to represent some square patch sitting somewhere outside of the radius of maximum winds. Now we're using the CM1 model, which is different than the one I described a second ago, but it's basically the same. We're using a Deardorff subgrid model, which is common in atmospheric sciences. The simple one, we're on a 1024 squared by 512 grid, so it's like 5 meter grid spacing, which is pretty high resolution for what we're trying to do. And then we inject spray droplets. So now, the color is saying something about the size. This is looking from the side. This is looking down on top of the domain. Each of these droplets, over a 5 by 5 kilometer domain, we can't track every spray droplet for obvious reasons, I hope obvious reasons. So we have this super droplet multiplicity, or I forget you were calling it something earlier, this to pick something.
Oh, MP pick.
Yeah, where basically each one, there's just some gigantic number that you're multiplying. However much each one of these droplets evaporates, you take that amount of mass and you multiply it by like 1 billion to get the actual amount, because that droplet is representing like 1 billion droplets with the exact same parameters. We're injecting droplets from the bottom using what's called a SSGF, a sea spray generation function. We take one of them out there, so at Andreas, the same Andreas, and then we augment it with some wind wave tank measurements, which suggest that there's a whole lot more large droplets being formed than some of the estimates there. But it's relatively, what I'm going to say is relatively insensitive to exactly what you do. The bottom is flat, as you can see, so we're still not resolving waves. So what we do is each new droplet, the SSGF is telling you how many droplets are being produced per unit area per unit time. So you enter these in, randomly at every time step, and we give it a height randomly between 0 and 10 meters, as though it could have been generated on a wave anywhere between those heights. I'll quickly note that this is part of a project where I was working with some software engineers and George Bryant to GPUize CM1, because NCAR built their newest supercomputer, like 30% of it, I think, 25–30% of it is GPU. They were working with groups to try to GPUize their codes to actually, ensure that the university community would use it. And so we did it for this. When they approached me to get involved, I said, yes, absolutely, as long as I can put my particles on there, because I think that GPUizes very well. And indeed, we've done scaling, and there's a paper out there if you're interested. These are using OpenACC directives, and so it was fairly low, lightweight to do. But a 1024 squared by 512 grid, I think the highest wind speed, we have like 3 billion particles floating around. On 128 GPUs, so V100s, NVIDIA V100s, the simulation completes within the 12-hour wall clock limit, which is, this is kind of an unfair calculation, but based on some of the comparisons of timing, that would be like, to get it done in that amount of time would require like 80,000 CPUs. And it's a little bit of a disingenuous comparison. But it's fast and efficient, because especially the droplet solver, the GPU can just rip through it really, really efficient, because they don't talk to each other. So it can just kind of do it,
But the way coupling doesn't.
You do have to compute, you have to send back the coupling force. So it's sequential, right? So it's got to do the flow solver and then wait for the droplet solver to send it back. There are tricks you can play there, which we haven't explored. Okay, so I'm ending soon, but really quick. All right, back to this picture. if you say, all right, let's just rearrange these expressions. This again, but back to the beginning of the talk, these are what you would like to know because these are what someone would have to put in their simulation. You can stop and just ask the question, how might spray change any of these based on these definitions? And so the answer is, all right, the numerator here is just the total flux. And you can say, well, all right, you've got your turbulent flux. You've got the spray itself carries momentum and sensible latent heat. So like obviously one way that spray can change them is by actually carrying a flux that needs to be parameterized. But in addition to that, it can also change the turbulent flux, right? Because if you cool or humidify the background, you'll actually change the correlation of the turbulence with these scalar fields. And, all right, so the direct flux, then this, and when you're talking about the flux coefficient, you can also change the reference state. You can actually change it potentially the 10-meter wind speed or temperature or humidity. Because again, if you're humidifying or cooling, you might change any one of these things. So we can take these large eddy simulations and we can just directly compute all of these terms and see what it does to these flux coefficients to see what's going on, right? We don't have to rely on these bulk flux models like Andreas's and so on. So I'm showing it for CH, the sensible heat flux. So what's plotted here, so all right, there's several things going on. 4 colors are referring to the 4 different wind speeds. The highest wind speed is blue, so maybe we'll just focus on that one. The light colors are the spray laden. Spray starts injecting at 30 minutes into the simulation. The dark colors here it is just no spray cases, and we want to compare the two. So at 30 minutes we start spraying, we see this massive shock to the system, and then it kind of levels out. That's the numerator, that's the combined spray and turbulent flux. If we look at the denominator, or just this term, we see that as soon as you start injecting spray, it cools it, which sends this difference up, okay? But what happens is this goes up and that goes up, and so then the flux coefficient itself actually kind of hovers around what it was to begin with, right? So you're increasing the numerator for sure, but you're also increasing this difference here. And so you're actually getting an overall effect, which is somewhat muted. The exact same thing happens with the latent heat flux. The total combined actually goes down slightly for reasons I don't have time to get into. The difference, the reference difference, drops as well, and in exactly the same way, you get something that actually doesn't change very much at all, which is kind of wild. And so if you plotted, CE and CH versus wind speed, like I've shown several times, the dark and the light are with and without spray, and there's hardly any difference. Within uncertainty, you're not seeing anything. In fact, out here at 55 meters a second, there's hardly any difference in the flux coefficients, which is not at all what these said, right? This was suggesting that you get out to some huge value. But there's something that I'm hiding from you, and maybe you picked up on it, and maybe I'll end there. If I go back, maybe I'll just stop, here. Those numbers that I just showed you here is the average over the final hour of the simulation. But I've completely skipped over this giant spike sitting up here. And what's happening is, what I'm showing you, this is the relative humidity. This is where spray starts, so it's quite dry, 87% relative humidity in the boundary layer. 20 minutes after you start injecting spray, it humidifies it and actually saturates it. And these are saline droplets, so it doesn't get quite to 100%. So what's happening is that the spray, right at the beginning, is evaporating like gangbusters, and then it saturates the boundary layer and then just kind of cuts itself off. And you have to ask the question, is this even realistic? Because if you take dropsons and you plot relative humidity versus height over different radii, like locations of the storm, you don't get a profile that looks like this. Like in reality, the storm is actually not saturating it. And so I think that just means we're missing physics, because a lot of the moisture would actually be going into the eye wall and then up the eye wall. And with this little patch, we don't have the means to be able to do that. So if we look at this, if we said, let's say if we just take this and this, these early times, and say that's what the spray would be experiencing, kind of normally, like it would be injected into a relatively dry layer, not a saturated layer, which is what's happened out here, then you get, skim over this, then you get something that actually starts to look more like this, right? So if now I'm just taking sort of like 10 minutes after spray injection starts, you start to do this, which, by the way, I'm going to kind of close by saying, I've been ragging on Andreas's model this entire time, but the name of this paper is called like the fallacy of spray-mediated enthalpy flux. And this is a whole lot of effort to basically show what he meant by the fallacy was that the spray flux was not only a function of wind speed. You have to take into account the ambient conditions, which is precisely what we just showed with these. And so it turns out he was actually onto something. And that you need to take this into account, like the background thermodynamic conditions, if you're going to say something about this. So instead of doing a proper conclusion, like we used drop zones to test sensitivity, test the bulk models, did the alias of spray, I will just quickly say, Martin mentioned this, we have this ONR MIRI that just kicked off last October. And what we want to do is go out and measure things. So the acronym is Sasquatch. So you can see in the top, and there's like the silhouette of Bigfoot. Study on air-sea coupling with waves, something. It's a really tortured acronym, but I really like it, even though I can't always remember it. So here's the NOAA P3, it's dropping its drop sounds and so on. But now what we have, the plan is to fly ocean drifters and wave drifters out and drop them ahead of the storm. And so that, hopefully we have a decent forecast, the storm will go over them, and at the same time, we're gonna be launching autonomous aerial vehicles that can go and fly above it, which could measure fluxes. And I'll just kind of close with this video from the company, Black Swift Technologies, that they created this animation of what this is doing. So that's the NOAA P3, like this is the aircraft at 2 kilometers or whatever. And they're designed to be launched through the same port that the drop signs go out. So there goes the tube, which now contains one of these drones. It unfolds itself and takes off. And you can fly, you can sort of, do step descents down to the surface. Now, this thing weighs 3 pounds and, it's going to get tossed around. But the idea, they're getting what seem to be fairly reliable measurements of momentum flux as computed by Eddy equivalence. Okay, and with that, I will stop. So we're going to do that in the upcoming season, assuming NOAA still exists. All right. Thank you.
Questions?
Yeah.
In your LES, I was curious, what is so the droplets here are Lagrangian, but of some size. What kind of scales do you think you're resolving in the turbulence?
Yeah, I mean, they're huge discrepancy, right? The grid spacing is like 5 meters.
Okay.
And so you've got a 20 micron droplet in a 5 meter grid box. And so I'm not even bothering to put in a subgrid correction because it's just going to be random noise at that point. It's not nearly the same sort of
But these are sub-Kamagra droplet sizes?
Yes, the Kamagra scale might be 100 micron in these kind of situations. I mean, the dissipation rates are high to the point where the atmospheric models actually, in the temperature equation, you actually have to retain the viscous heating term because the dissipation rates are so high. So it's close, I would say.
What's your Reynolds number, do you think?
Or if infinite, I don't know. I mean, yeah, I don't actually know. I mean, I don't, sometimes I get mixed up as to what height scale you want to use, but it's in the V8, something like this.
So in an energy spectrum, you're like cut off as way to the left on the,
Right.
you're not resolving most of the inertial subrange.
No, I think we are.
You're resolving most of the inertial
Well,
subrange for Reynolds number 10 I guess you know what you could do is you're using some type of eddy viscosity in your LES.
Right.
So what's the ratio of the eddy viscosity to molecular viscosity?
Yeah, I mean, it's gigantic. In fact, the molecular viscosity is not even in, it's not in the code. Right, we don't have both of them.
Okay.
But I mean, it's not even close.
Yeah.
I mean, it's 4 orders of magnitude different or something like this.
In the spray, similar like the 5 kilometer one, why the spray start at 30 something? So
30 minutes?
I forgot.
Oh, 30 minutes into it?
I forgot what the unit, but
Yeah, I wanted to let the turbulence develop, right? So like we start with an initial profile of heat. Like there's an initial condition, but there's no turbulence to begin with. So I want the turbulence to kick in before we start injecting the spray. The problem that I was kind of hinting at. So one of the things I was gonna say, like, so the initial condition for the relative humidity at the beginning is actually this red curve. It's this one right here. That's how it starts. But then it quickly deviates from that because I haven't yet started injecting spray, and then I inject spray into something that's different than what I had intended to do here, and that's I'm still not totally sure how I want to do that, but I have to let the turbulence develop before I start injecting, because I think I'll start confusing things if I don't.
will the result different for different injection time?
I think as long as I wait. I think if I inject it like way back here, I might see something different, but I think I would not trust it. But I think any time beyond here, like 20 minutes, I think no matter where I injected it, I think I'd get the same result. That at the beginning, you'd get a spike, and then it would saturate the layer, and then you get something that relaxes back to the interfacial of the spray-free condition. So I don't think the conclusions would change at all. Yes.
So you have these graphs of, I think, CD and some other quantities which are constant at first, and then for U10 greater than 40, they start to go up linearly.
Right.
So what happens at that point? Is it
So like this.
Yeah.
Yeah, no idea. I don't know, and they don't know.
Okay.
And it's a wind tunnel, so you can start asking questions like, well, I don't know. I mean, what makes a kink like that? I really don't know. And as I was saying earlier, these diamonds here, we suspect based on some of this. What I was saying here was that that's these points, these same points. It seems that what they're measuring is the interfacial flux because they're blowing spray out the back and not accounting for it. And so is that also happening in that Japanese tank? Possibly. I mean, there's a ton of spray. I mean, if you look at a video of this, and there's just a ton of spray going out the back. And if you're not accounting for it, then I don't know how that would lead to a kink. I don't have an explanation for that. But that's where it's like, I look at these pictures like this, and I don't think this is true. Or actually, no, I take that back. If you combine that with what I just said about the ambient conditions, maybe the other thing too is that maybe it's quite dry in the lab, and that the spray actually is being accounted for, and it's actually exaggerated because it's much drier in the lab than it would be in a saturated boundary layer. That might be happening as well, and I don't think either of the laboratory groups know that for sure.
Why do the relative humidity profiles kind of reach a shape that's
Weird looking?
yeah? What does like the boundary layer look like, or what?
Yeah, so you have to keep in mind that this is a kilometer tall, and so the water vapor mixing ratio gets mixed out with height, and the potential temperature is the conserved energy variable, which is uniform with height. But then the density and the pressure and the temperature go down with height, and so it's relaxing to that. So this profile is actually the well mixed profile in an adiabatic, an isentropic hydrostatic background.
Mhm. Yeah, it actually kind of looks like the purple one here. I didn't realize that guild. Yeah.
Right. And what I'm writing a 2-part paper on this right now. And what we show is that once the spray gets injected shortly after, you actually start recovering mean Q and T profiles that sort of undoes this somewhat unrealistic. So if you just let the thing go without any spray, it wants to just mix everything out, and that's not what the temperature, the drop zones look like. And that's easier to see when you plot Q and the potential temperature. But when you add spray, both of those profiles start to look a whole lot like what the drop zone profiles look like, which is, it's like, oh, that's interesting that the spray might actually be the thing that you need to get the shape to be what it needs to be. And so we're still kind of exploring that.
Do you know anything about the residence time of the spray once
Oh.
it gets injected, and
Yeah.
how high would it go?
Yeah, okay, so I know we're already over, so apologies. That's actually, I skipped over this. That's precisely the advantage of using the Lagrangian method, that we can count this. If you recall, the assumption behind these bulk models is that every droplet, at least every droplet worth considering, is quote reentrant. And so I was trying to use the bulk method to test the LES results, and I was getting weird answers. I mean, to the point where I actually thought I had done something wrong in the LES. And what I realized was that enormous amounts of mass are just leaving the boundary there. They're just going up. So the lifetime is infinite almost. And so huge amounts of mass, you know, the total droplet mass in there is going up with time and just continuing. You're pumping more and more in, and they're just flying away from the surface. The DNS where we had done this has a lid on the top. They're assuming that in this model, and that seems to be a completely incorrect assumption about this. And so one of the things in this second part of the paper that I'm doing now, we're trying to kind of demonstrate this, because in the model too, so again, you have to parameterize how much it's going to change its temperature and mass. So what they do is they say, all right, we need to know what the lifetime is. So what they say is, we'll take the significant wave height, and the time is just how long it would take to fall at its Stokes terminal velocity down to the surface. That's not true.
No, it's not
That's not,
correct.
yeah, well, and it's like, and it's going horizontally, right? And it's kind of, you know, it might hit a wave in front of it before. And so we're looking at distributions of lifetime and pointing out that that estimate is also not even close to being correct. So small droplets, you know, let's say radii of 100 microns or less, have a uniform distribution anywhere between like immediately dying all the way out to the end of the simulation. And it's a uniform distribution, so a droplet could be anywhere inside, and it's most certainly not just, you know.
Well, you know the evaporation time scale, right?
Mhm.
So you could look at the ratio of the
Yep.
time scales.
Yes, which is partly how they justify looking only at large droplets, which they assume to be doing, you know, falling back in. And that's exactly what we did in the DNS, is we were looking at exactly that ratio to see how long it lived relative to how long it could have changed its radius. So Andreas and others are certainly aware of that, but the problem is that even a large part of the problem is that the small droplets which get neglected, there's just a ton of them. So there's a huge amount of mass which is just being unaccounted for in that budget, even though they're small and even though they're living so much longer than their radius time scale. There's just like billions of them. So I'm sorry, I'm getting like excited now, but yes, this is like what, I mean, this is kind of one of the primary things that we set out to quantify at the very beginning. Yeah.
So you're getting these coefficients, right? Say, yeah, I guess there's a big picture thing. So, is the idea then that you can use these coefficients to predict like hurricane trajectory?
Yes, and actually, you're making me realize that I actually did forget like the most key result, like conclusion to sort of summarize things. And it's that, oh my God. So yes, the answer to that is yes. The idea is like, okay, what now would I turn around and tell, I mean, Christian, or someone who runs these kind of global scale or mesoscale models, here's what you need to do at the bottom surface to get the correct amount of momentum, heat, and moisture being carried in. From everything I've done, what you cannot do is assume that all you need to do is just make a different choice of CK, and there, you've done it. And again, I'm certainly not the first to do this. Like, it can't just be like, oh, does it go up to 4 times 10 to minus 3, or does it stay flat? What you need to do is you have to have an interfacial flux and a spray flux, which have to communicate with each other, which is exactly what like Ben Barr has done in, you know, using WRF and so on. But yes, that's Ben and I, that's exactly that exchange that you're talking about. I tell him like, okay, what I'm seeing is that this is the way that you need to do it. Like this, you know, this model where this bulk model where you're just accounting for delta M this way, you're missing this much. And then he's like, okay, I'll adjust my model so that I get the right amount of spray that, or sorry, I'll get the right amount of heat and moisture being transferred in and out.
How big of like an influence, or how sensitive are these trajectory models to these coefficients that you're?
Yeah, and that was, maybe I'll just go back to here. That's kind of what these were trying to show, is that they're actually very sensitive to them. So, I mean, again, this is just Vmax as a function of time with a bunch of different choices for CK and CD. And you can get storms that don't develop, or you can get ones that develop too quickly. And so it actually is quite sensitive. Even from a bulk point of view, there is this relationship that, depending on how strong you make CK relative to CD, you actually just systematically increase the storm strength. And so it is sensitive. You want to know what it is, even though I'll also say that it's not just simply, oh, here's what you should be using for CK instead. You have two mechanisms that are pumping stuff in and out, and you have to treat them separately. Sorry, another thing I realized I forgot to say, I didn't show at the end with the LES, I didn't show any drag coefficient because it does nothing.
I was gonna ask about that.
No, it does nothing to it. So I think all those models, like I showed at the beginning, this one, this spray only shows that CD rolls off, I think is not correct. And you read it, there's some faulty
It's pretty
assumptions.
flat, that part.
Yeah. The idea, there's a whole Russian group that, has anyone heard of the Kolmogorov number? So Baron Blatt kind of coined this. Baron Blatt was Kolmogorov's last student. He would show up to seminars at Stanford when I was there. What he did, with thermal stratification, if you have stable stratification, you can damp out turbulence. And what Baron Blatt did some work on was like, oh, if you have suspended dust or something, the effective mixture density, you could get a stable stratification, not due to thermal fluctuations, but due to concentration fluctuations. And so the equivalent to a Richardson number, he coined the Kolmogorov number in honor of his advisor. And so you can get thermal stratification due to this. And then he and Lighthill came up with this idea that, oh, well, maybe that's what's going on. You have all this spray at the bottom, like near the surface, and less above. And so that's a stable density gradient. And so that's the basis for some of these models. But they're using extremely unrealistic concentrations of spray in order to get this. And one of them, they think they incidentally use like 10,000 times as much spray injection as what some of these SSGFs propose out there. So I don't know how realistic those are. Sorry, now we're way over. I apologize.
And there's not one picture of Trump with a Sharpie.
Oh, yeah, missed opportunity. I didn't even think about it. Right. No, they are, so this is an ONR funded MURI. I mean, we're in planning stages to go out and fly into these hurricanes. We're coordinating with the Air Force, and so part of the group, they have connections that are gonna drop all these things out ahead of the storm. I hope to get on a flight and launch these SCOASs and make these flux measurements, but we're relying on the NOAA flights. And I mean, they are proposing shutting down the NOAA labs, which includes AOML, which is where the Hurricane Research Division sits. And if that were to happen, I actually don't know what, again, the funding, ONR still, the project still exists, but I don't know what we do then.
This summer?
Yeah, well, they're proposing shutting them down next year, so we might get this season in.
Yeah, but you wanna measure a couple of summers then?
Yes, we want to do this summer and next summer. We have funding and sort of equipment for doing this season, which, hurricane season's like June to October. And we want to do it again next year, and that's where it's really up in the air. So we'll see.
One last question.
Yeah.
In the
Well, that's
oil level
talk off.
simulations, what is the volume fraction? Highest volume fraction?